Hello everyone, my name is James Thorne. I'm here to present our recent work on neural databases and the operator model that's at the core of a recent paper we've made available on arXiv since submitting to this summit. Our objective is to scale neural reasoning to answer queries over large databases of facts stored in text. This is something that is not possible with current NLP models, such as those used in OpenBook question answering. The key challenge of neural databases compared to OpenBook QA is that in order to support database-style operations, such as aggregation, we need to consider using many, if not thousands, of facts, perhaps without direct supervision as to which facts are needed to answer the query. The first set of baseline experiments used the widely adopted sequence-to-sequence neural architecture with a transformer model. All facts are jointly encoded together with the query, and the model is trained to generate an answer with full supervision. Unsurprisingly, this model performs well on our synthetic dataset for most query types. For questions where a Boolean or extractive answer needs to be returned, the accuracy is above 99%. This model is even capable of performing something analogous to a join, where multiple pieces of information must be used together in order to answer the query. While this model worked well for simple queries, there are cases where the model is not accurate. This is namely the counting operation, and where multiple facts must be extracted. For example, a query such as list all celebrities who have won an Oscar. A second limitation is that due to the quadratic memory complexity of self-attention, the model cannot scale to more than 1,000 tokens without modification. This would limit us to encoding databases of approximately 50 facts. Combining information retrieval, such as DPR or TF-IDF, does work well for Boolean and extractive queries. However, for aggregations, this additional retrieval step harmed accuracy. Also, this limitation would still prevent us from asking queries that aggregate large numbers of facts. To overcome this limitation, one could use Fusion in Decoder, which would reduce the memory complexity. However, the interfact self-attention is required during encoding, as late fusion harmed the accuracy of answers which join or aggregate multiple facts. Additionally, for queries combining multiple facts, the model suffered from an oversensitivity to irrelevant facts, as removing unrelated information with erasure-based adversarial attacks caused the model to generate incorrect answers. The innovation in neural databases is to perform a query-based derivation of the facts stored in free-form text to a machine-readable form before using non-neural functions to aggregate the result. In our case, the NeuralDB operator is a transformer model that is trained to perform high-precision selection, as well as project the fact to an intermediate representation. This both overcomes the encoder limit and results in a more stable model, as the operator is only trained to extract information rather than synthesize answers. In both Oracle and IR settings, we demonstrate that the model has higher accuracy than end-to-end neural approaches over queries requiring combinations of thousands of facts. This is something that would have been impossible in the baseline. In our recent paper submitted to arXiv, we further allude how we can use distant supervision to train the IR step, which has comparable accuracy for most query types. These experimental results are exciting and show potential for the NeuralDB architecture. Future work will focus on supporting a wider gamut of query types and extending to a wider diversity of language. Thank you very much.